Okay, this is the second video, chapter 3. Newton's law of universal gravitation. Should be now here with the graphic blocked out. Basically, Isaac Newton, he's famous for the picture of him sitting underneath an apple tree with the apple hitting him on the head and going, ooh, gravity. It's true. And basically, what he started thinking about is he was underneath the apple tree and the apple falls and hits him on the head. Whether it hit him on the head or not, whatever. But he basically said, why did the apple fall and hit me? He goes, it must be attracted to me. And then he's thought, well, I must be attracted to the apple. And I am attracted to the earth. But because the earth is so big, its attraction to me is stronger than my attraction to the apple. All right? So it has to deal with the differences in mass and the distance away. Okay? Those are the big things. So he said when this happened, he kind of started looking up at the sky. He started looking at the stars and the sun and the moon and everything. And he realized that we are attracted to everything. Okay? And then Newton's universal law of gravitation is simply put, it's an attraction law. It's not a repulsion law, not like electrostatics. You can attract or repel, or magnetism, attract or repel. This is attraction only. Okay? And gravity attracts based on mass and the distance between them. Okay? So the mechanisms in Newton's law of universal gravitation is point mass m1 times point mass m2 divided by the distance between the point masses, or the centers of the mass of the object, okay, squared, all right, times this g. Now this g is not gravity, not 9.81. This is 6.67 times 10 to the minus 11th newtons meters squared over kilograms squared. So the universal G is a number that was calculated many years after Newton's death. When Newton first wrote the formula, he said all forces are attracted to each other equally, and the force of attraction is based on the two masses involved and the inverse squared of the distance between them. And then he had put a question mark here instead of G. He said, I know there's something I'm missing, but I don't know how to calculate it because I don't have the technology at the time, or he needed some help. Okay? And in his memoirs that he wrote, he put a question mark where this G was. He knew there was something else there that wasn't quite right, but he knew it was really, really small. Okay? So he ends up, it says, Newton's law of universal gravitation is a physical law describing the gravitational attraction between bodies with mass. Every point mass attracts every other point mass by a force pointing along the line intersecting both points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between the point masses. So this is the master formula that came out. F equals big G, right? Little g, that's 9.81. Big G, 6.67 times 10 to the minus 11th, times mass 1 times mass 2, divided by the distance between the centers squared. Okay? Now, this formula tends to be kind of tricky to calculate, especially when you start using like the mass of the earth, the mass of the sun, things like that. Okay, because your numbers get really, really big, and then people will get the old scientific calculator out and they'll start plugging everything in. Couple hints. If you have to calculate force, which you will, use parentheses, only do the numerator, get an answer, and then hit divide by the denominator, all right? And don't forget to square it. All right, when you have your test question and I'm asking you, I guarantee you one of the choices I'm going to give you is this question with this not squared. All right, it'll be a wrong answer and you'll think you got it right. I'm telling you right now, I'm going to do it to you because I want you to make sure you do it right. All right? All right. So F is the magnitude of gravitational force between 2-point masses. G is the gravitational constant. M1 and M2 are the masses, and R is the distance between them. And remember, it's squared. Okay? Assuming SI units, F is measured in newtons, M1 and M2 is kilograms, R is in meters, and G is 6.67 times 10 to the minus 11 newtons meters squared over kilogram squared. That's why it's a negative 2. The value of constant G was first accurately determined from the results of the Cavendish experiment conducted by British scientist Henry Cavendish in 1798. Though Cavendish himself did not calculate G, he did the activity that gave tons and tons of data, which then they used to calculate G. All right? This experiment was the first test of Newton's theory of gravitation between masses in the laboratory. It took place in 1798, 71 years after Newton's death. All right, so Newton never even got to find that little piece that was missing. Probably drove him nuts. Okay, so none of Newton's calculations could use G. It could only calculate a force relative to another force. And what they would do is they, the little sideways. I was called the little Jesus fish thing. Looks like an alpha on its side. It means proportional, and they some old like documents from like the 1700s and 1800s where they would write F equals, instead of equals, they would do the little proportional to M1 M2 over R squared. All right, because they knew there was something missing. Anyways, the Cavendish experiment was done in 1797 to 1798 by Henry Cavendish. It was the first experiment to measure the force of gravity between masses in the laboratory and the first to yield accurate values for the gravitational constant and the mass of the Earth. However, these were derived from others from Cavendish's result, which was the value for the Earth's density. Okay, so this is a little picture of Cavendish's setup here. Okay, he had extremely large masses. He had a balance, all right, that you could see the needle, and it was in a closed shed. He built a shed, okay, and then he had little pulleys and stuff to actually oscillate these masses, and then he could, from the oscillation of the masses, he could calculate the dampening effect of the gravitational pull of the Earth on these masses. It was really amazing, and he did this all before 1800. Okay, so he performed the experiment inside a closed shed and observed results through a telescope. So he had a little telescope in here, and that's what he would look at, see everything going on. All right. The opening in the wall was added by the artist to show the apparatus. Cavendish's only goal was to measure the density of Earth. He called it weighing the world. All right. Now think about how brilliant this guy had to be, that he could come up with something like this before 1800. We didn't have stopwatches back then. Everything was just so archaic, and just actually to do all the things that he did is absolutely mind-blowing. It really is. Kind of just, I'm totally amazed. All right. G. Okay, so here's a little question we're going to do for ourselves. Calculate the force of attraction between the Earth and the satellite Zoltar. The mass of the Earth is 5.972 times 10 to the 24th kilograms. The mass of Zoltar is 1.2 times 10 to the 6 kilograms. And the distance between them, and I'm nice, I gave you 13,500 meters. I didn't put it in kilometers where you'd have to convert or anything. Okay? So I want you to try this out and see what you get. I'm going to do it on my calculator right now. And don't forget the 6.67 times 10 to the minus 11th, okay? Did you get that? All right. So I got 2.62 times 10 to the 12th newtons. That's the force of attraction between them. Okay. If you didn't get that answer, 2.62 times 10 to the 12th, two common problems I've seen for the last 25 years doing this. When you're setting things up in your calculator, if you use the caret symbol to do like 5.972 times 10 caret 24, you have to have the whole thing in parentheses. And then go times 1.2 times 10 to the 6th in parentheses times the 6.67 times 10 to the minus 11th in parentheses. Hit enter, divide by 13,500 squared. Okay? If you do that and you get it right, perfect. I use the EE button. Oh, look at that, it's reversed. Okay. I use the EE button on the calculator. It's the second function comma. And what I do is I type in 5.972. I hit EE and then 24. Okay. By doing that, it tells the calculator that it's times 10 to the 24th. I think it's a lot easier. And then I get my answer in terms of E. All right. So, anyways, give it a shot. Make sure you know how to do that. You're going to have one of these on your test. All right. All right. Relationships. What happens if you triple the distance? Think about it. You got two objects here. We triple the distance. All right. The distance is on the denominator. It's squared. So if I triple it, 3 squared is 9, and it's on the denominator. So your force is 1/9. All right. How about if I have it? I have the distance. Make it closer. If it gets closer, it goes up. If it gets farther, it goes down. If it gets closer, it goes up by the square. If it goes farther, it's a fraction by the square. Okay? So let's say if I have half the distance, all right, that would be 4 times as great. 2 squared, 4. If I have 1/3 the distance, 3 squared is 9. 9 times as great. Okay? How about if it's 1/4 the distance? All right? So 1/4 means it's getting closer, it's going up, and 1/4, that would be 16 times stronger. What if you were 5 times the distance, made it real far away? What's 5 squared? 25? So it'd be 1/25. That's how you do that. What happens if you double the mass of a satellite? Well, that's the direct relationship. You double mass 1, it's just doubled. You double mass 2, it's just doubled. If you double them both, it's double times double, which is 4. Okay. Okay. What happens if it's what happens if the satellite's half away, half the distance away? 4 times stronger. Okay. All right. Thank you.